From a distance, the moons of the outer solar system appear sealed and motionless. They circle far beyond the warmth that shapes Earth's rivers and rain. Their surfaces are pale with frost, crossed by fractures, darkened by radiation, or buried beneath layers of frozen material that have endured for millions of years. Nothing about them seems to suggest an ocean. There are no blue horizons, no waves reflecting sunlight, no clouds rising from open water. On these remote moons, the sea is hidden beneath the ground. Somewhere below the ice of Europa, water may surround the moon in a global layer deeper than any ocean on Earth. Beneath Ganymede's battered surface, several layers of water and high-pressure ice may be stacked through the interior. Callisto, older and more heavily cratered, also appears to contain a buried liquid reservoir. Farther away, at Saturn, a moon scarcely wider than the distance between two neighboring cities sends its ocean into space. Enceladus releases fountains of water vapor and ice grains from fractures near its south pole. The material rises above the surface, spreads along the moon's orbit, and helps supply one of Saturn's rings. A spacecraft passing through those plumes was able to sample particles that had begun their journey in a sea no human instrument had ever touched directly. Titan hides water differently. Its surface holds lakes and seas, but they are made largely of liquid methane and ethane. The water there is locked into rock-hard ice. Deeper below, however, evidence points toward another ocean, separated from the cold landscape by a thick, frozen shell. These worlds have changed the meaning of a habitable place. For much of scientific history, liquid water seemed to belong near the sun, where warmth could keep it from freezing. A world too distant from sunlight appeared destined to become solid from surface to center. But a moon is not warmed by sunlight alone. Gravity can bend it. An orbit can squeeze it. Radioactive elements within rock can release heat over immense spans of time. Salts and other dissolved materials can lower the temperature at which water freezes. Beneath enough ice, pressure can shelter liquid from the emptiness above. The outer solar system, once imagined as a region of permanent frost, may contain more liquid water than the familiar planets nearer the sun. Yet none of these seas can be seen in the ordinary sense. Their presence has been inferred from magnetic fields, gravity measurements, surface geology, changing rotation, heat escaping through ice, and particles carried into space. Each clue is indirect. Each arrives through an instrument designed to notice motions or forces too small for the human body to feel. The oceans remain below. They may be dark from shore to shore, with no sunrise at the surface and no wind passing overhead. Some may touch warm rock. Others may be trapped between layers of ice, separated from the minerals that could support useful chemistry. Their depths, ages, and compositions differ from moon to moon. And somewhere within those differences lies one of the most important questions in planetary science. Not simply whether water exists beyond Earth. We already know that it does. The deeper question is what happens when water, energy, rock, and time are enclosed together beneath a frozen world. Tonight, the journey begins above the ice, among moons that seem silent from afar. Then, one layer at a time, the view will move downward, beneath old craters, beneath broken plains, beneath shells that flex under the pull of giant planets, towards seas that have never known an open sky. For a long time, the idea of oceans beneath ice belonged more to imagination than observation. The moons beyond Mars were known first as points of light. Through early telescopes, they appeared as small companions, moving around Jupiter and Saturn. Their paths could be measured, their brightness could be compared. Their repeated motions helped reveal the scale and order of the solar system, but their interiors remained inaccessible. Even when larger telescopes began to resolve their surfaces, the images offered only hints. A bright patch might be frost, A dark region might be older material. A line across the surface might be a crack, a ridge, or an artifact of distance and atmosphere. The first strong changes came when spacecraft began to pass close enough to measure more than reflected light. A flyby does not need to enter an ocean to detect one. It can watch how a moon bends under gravity. It can measure how the moon's magnetic environment changes as it travels through the field of a giant planet. It can track the exact shape of the surface, the distribution of mass, and the way heat escapes from particular regions. These measurements are quiet in their raw form. A slight change in a radio signal, a shift in a magnetic reading, a fraction of a degree in the orientation of a crust, a narrow warmth beneath a dark fracture. Yet together, they can reveal something as large as a global sea. Europa became one of the earliest and most compelling examples. Its surface is strikingly young by planetary standards. Compared with heavily cratered moons such as Callisto, Europa carries relatively few large impact scars. Its ice is crossed by long bands, ridges, and broken terrains where surface blocks seem to have shifted, rotated, and settled into new positions. The crust does not look like an untouched shell. It looks renewed. Some regions resemble packs of sea ice viewed from high above, though the scale is much larger and the material is water ice, rather than floating sheets on an open terrestrial ocean. The resemblance is useful, but only as a beginning. Europa's geology formed under conditions of lower gravity, colder temperature, and repeated tidal stress, unlike anything on Earth. The crucial point is movement. A rigid, frozen body can crack. But Europa's surface appears to have done more than crack. It has spread, separated, and rearranged. In some places, younger material seems to have risen from below and filled gaps between older blocks. That suggests a warmer, more mobile layer beneath the exterior. The evidence became stronger when the Galileo spacecraft studied Europa's magnetic environment during the 1990s and early 2000s. Jupiter possesses an immense magnetic field. As its moons move through that field, electrically conductive materials inside them can respond. A salty liquid ocean is conductive. It can generate an induced magnetic field that changes with Jupiter's own rotating magnetic environment. Galileo detected variations around Europa consistent with such an effect. The measurement did not produce an image of water. It revealed the electrical behavior expected from a broad layer of conductive liquid below the surface. Salt matters because pure water is not a strong conductor. Dissolved ions allow electrical currents to flow more readily. The magnetic evidence, therefore, pointed not only toward liquid, but toward water containing dissolved material. The exact thickness of the ice shell remains uncertain. Some models allow for a relatively thin crust above the ocean in certain regions. Others suggest many kilometers of solid ice, possibly with warmer and more deformable zones beneath the rigid outer layer. The interior may not be uniform. Different regions may carry different temperatures, structures, and histories of resurfacing. This uncertainty is part of the science. A hidden ocean is not a single fact followed by a finished explanation. It is a system of connected questions. How deep is the water? How salty is it? Does it meet the rocky mantle below? How often does material move between the ocean and the surface? How long has the liquid remained stable? Each answer changes the picture of what the moon could support. Ganymede introduced another kind of evidence. It is the largest moon in the solar system, larger than the planet Mercury. It also has its own internally generated magnetic field, something no other moon is known to possess. That field complicates the measurements around it, but it also makes Ganymede especially revealing. Observations indicate that a conductive layer lies beneath the surface. The most likely explanation is a salty ocean. Yet the pressure inside Ganymede becomes so great that water may be arranged in several forms. Nearer the surface, ordinary ice may form the outer shell. Below that could lie a liquid ocean. Deeper still, pressure may compress water into denser phases of ice that cannot exist naturally at Earth's surface. Another liquid layer may lie beneath one high-pressure ice layer, followed by another transition farther down. Instead of one ocean above rock, Ganymede may contain a layered interior where liquid water and dense ice alternate across hundreds of kilometers. This structure raises a difficult question. On Earth, ocean water touches a rocky seafloor. That contact allows minerals and dissolved chemicals to enter the water. It also creates places where heat from the interior can drive reaction. If part of Ganymede's ocean is separated from rock by high-pressure ice, the movement of chemistry may be more limited. But the model is not settled in every detail. Depending on the composition, salinity, and thermal structure, some liquid layers may still interact with deeper material. The interior may be more complex than a clean sequence of boundaries. Callisto offers a quieter version of the same story. Its surface is crowded with craters accumulated over immense stretches of time. It appears less geologically active than Europa. There are fewer clear signs of recent resurfacing and less evidence of a crust repeatedly broken and renewed. Even so, Galileo's magnetic measurements suggested a conductive layer beneath Callisto's exterior as well. A buried salty ocean may exist beneath an old, cold shell. This matters because it separates the existence of liquid water from obvious surface activity. A moon does not need bright plumes, young terrain, or dramatic fractures to retain an ocean. Water can survive under a surface that appears almost completely unchanged. The sources of heat are different from world to world. On Europa, Jupiter's gravity pulls strongly on the moon, while the gravitational influence of other moons prevents Europa's orbit from becoming perfectly circular. As Europa moves slightly nearer to and farther from Jupiter, the strength of the pull changes. The moon bends. Its interior is repeatedly distorted. That motion produces heat through internal friction. The process is similar in principle to bending a material again and again until it warms, though the moon's response occurs through rock and ice across planetary scales. The orbital arrangement that sustains this motion is shared with Io and Ganymede. Their periods are linked in a gravitational pattern known as a resonance. The moons repeatedly influence one another in ways that preserve their orbital relationships. This resonance helps maintain the small departures from circular motion that allow tidal heating to continue. Without it, Europa's orbit might gradually become more circular, reducing the changing gravitational stress and allowing the interior to cool further. The hidden sea therefore depends not only on Europa and Jupiter. It depends on a system. A moon keeps an ocean because neighboring moons help shape its path. Gravity moves through the entire arrangement, from one orbit to another, becoming pressure, deformation, friction, and finally, heat beneath the ice. The ocean is not isolated from the sky above it. It is maintained by motion through space. That connection is easy to miss when looking at a frozen surface. The water lies below, but part of its energy comes from the repeated geometry of the moon's journey around a planet. Far from sunlight, an orbit can become a source of warmth. At Saturn, the hidden ocean begins to escape. Enceladus is a small moon only about 500 kilometers across. Its surface is bright with water ice, reflecting much of the sunlight that reaches it. From a distance, it appears almost too small to sustain much internal activity. Yet near its south pole, long fractures cut across the terrain. These parallel cracks are often called tiger stripes. They are warmer than the surrounding surface, and from them rise jets of water vapor, ice grains, salts, and other materials carried upward from below. The ocean announces itself by leaving the moon. This changed the search for hidden seas in a fundamental way. Europa's ocean had been inferred through magnetism, geology, and orbital behavior. Enceladus offered something more direct. A spacecraft did not need to drill through the crust. It could pass through material already being delivered into space. The Cassini spacecraft first entered the Saturn system in 2004. Its mission had been designed before the full nature of Enceladus was known. The Moon was one target among many, and there was no expectation that it would become one of the most revealing places in the outer solar system. Early images showed the south polar fractures. Additional observations detected heat. Then, instruments measured plumes extending above the surface. Cassini's path was adjusted so that the spacecraft could fly through it. During those encounters, particles struck the spacecraft's detectors at several kilometers per second. The instruments could not preserve intact samples in the way a laboratory on Earth might, but they could measure the masses and chemical patterns of the material entering them. The plume contained water vapor. It contained particles rich in sodium salts. It contained carbon-bearing compounds. Some grains included silica so small that their presence pointed toward interactions between hot water and rock deep inside the Moon. Silica can form under a range of conditions, but the sizes and characteristics of the particles detected by Cassini were consistent with warm water, circulating through a rocky seafloor, dissolving material, and later cooling as it moved upward. This suggested that Enceladus does not simply contain liquid water trapped inside ice. Its ocean may touch rock. That contact is important. Water meeting rock creates opportunities for chemical reactions. On Earth, one of the best-known examples occurs at hydrothermal systems on the ocean floor, where heated water moves through fractured crust, collects minerals, and returns to the sea carrying dissolved substances. The environments on Enceladus would not be identical to those on Earth. The pressure, temperature, rock composition, and energy available may differ, but the broad physical idea is similar. Warm water circulates. Rock changes the water. The water carries evidence of that contact upward. Cassini also detected molecular hydrogen in the plume. One possible source is a water-rock reaction known as serpentinization. This occurs when liquid water interacts with certain minerals in rock, changing the minerals and releasing hydrogen. On Earth, hydrogen can serve as an energy source for microorganisms in places where sunlight never reaches. Its detection at Enceladus does not demonstrate that life exists there. It indicates that a known form of chemical energy may be available. The distinction is central. A habitable environment is not the same as an inhabited one. Water, useful chemistry, and energy can create conditions in which life might function. They do not tell us whether life ever began, whether it survived, or whether the necessary reactions occurred in the right sequence. Enceladus offers ingredients. The deeper history remains unknown. Phosphorus has also been identified in ice grains associated with the plume. It is a biologically important element on Earth, used in molecules involved in energy transfer, cell membranes, and genetic material. Its presence adds another component to the chemical inventory. Again, it does not serve as evidence of organisms. It shows that the ocean contains more than simple water and salt. The sea beneath Enceladus appears chemically connected to a rocky interior and capable of transporting material outward. The path from ocean to plume is still being studied. The south polar fractures may extend downward into the ice shell, but the exact structure of the channels is uncertain. Some models describe narrow conduits connecting the surface with liquid reservoirs. Others suggest that water may enter networks, cracks, partially freeze, boil under low pressure, and separate into vapor and particles before escaping. The plume changes with the Moon's orbit. As Enceladus travels around Saturn, tidal stresses open and close the fractures by small amounts. The flow appears to respond to this flexing. though the relationship between orbital position and plume strength is more complicated than a simple valve turning on and off. The same gravity that helps warm the interior may also regulate the release of ocean material. Enceladus is trapped in an orbital resonance with the moon Dione. This relationship helps maintain a slightly eccentric orbit, rather than allowing it to become perfectly circular. As a result, Saturn's pull changes over the course of each orbit. The moon is repeatedly squeezed and relaxed. That deformation generates internal heat. Because Enceladus is small, it should have lost much of its early warmth long ago. Its continued activity points toward tidal energy as a major source of the heat now escaping near the South Pole. The amount of heat detected has challenged simple models. A moon this small must balance energy carefully. If the interior loses heat faster than tides replace it, the ocean should gradually freeze. If tidal dissipation is strong enough, liquid water can persist. The thickness of the ice shell varies by region in many models. Near the equator, the shell may be thicker. Near the active South Pole, it may be thinner, allowing greater deformation and easier transport of heat and material. The ocean itself is widely thought to be global, surrounding the rocky core beneath the ice, though earlier interpretations considered a regional sea beneath the South Pole. Measurements of the moon's slight wobble as it rotates helped strengthen the global ocean model. A solid body attached rigidly from crust to core would not move in quite the same way. The observed motion is better explained if the outer shell is partly decoupled from the deeper interior by liquid. A whole sea may lie beneath the visible surface. Above it, the plume continues to feed Saturn's E-ring. This broad, diffuse ring is made mostly of tiny ice particles. Enceladus supplies them steadily, sending material outward until it spreads along the moon's orbital path. The hidden ocean, therefore, becomes part of Saturn's appearance. A particle can begin below the South Pole, rise through a fracture, escape the moon, and enter orbit around a planet. Some grains fall back onto Enceladus, some coat neighboring moons. Some remain within the ring, before eventually being removed by collisions, radiation, or gravity. The ocean is enclosed, but not perfectly sealed. Its material crosses boundaries, from water to vapor, from vapor to ice, from the interior of a moon to the space around Saturn. This movement creates an unusual opportunity for future exploration. A spacecraft could pass through the plume more slowly than Cassini did, using instruments designed to examine fragile organic molecules with greater care. It could measure the relative abundances of compounds, search for patterns that chemistry alone might struggle to produce, and compare material from different plume regions or different moments in the moon's orbit. Such a mission would still need caution. Complex organic chemistry can arise without biology. Mineral reactions can create molecules that resemble parts of living systems. Radiation can alter particles after they leave the surface. The route through the fractures may change the composition of the sample before it reaches space. Every signal would need to be separated from these other possibilities. But Enceladus offers something rare. It brings the interior outward. The surface does not merely preserve a record of what happened below. It releases active material from the present ocean. No landing is required to reach the first layer of evidence. No drill must cross kilometers of ice before the chemistry can be studied. The moon performs part of the journey on its own. There is a simple image hidden inside all this complexity. A small world moves around Saturn. Its orbit flexes its interior. Its rock warms water. Its ocean gathers salts and molecules. Then, narrow fractures lift a trace of that sea into space. The plume rises above the South Pole and catches sunlight. For a moment, an ocean that has never seen the sky becomes visible. Europa does not release its ocean as openly as Enceladus. Its surface holds the evidence close. From orbit, the moon appears bright, smooth in broad view, and crossed by reddish-brown lines that extend for hundreds or even thousands of kilometers. Some are narrow. Others form paired ridges with darker material between them. Many intersect without erasing one another, leaving a record of repeated cracking across different periods of the Moon's history. The surface is made mostly of water ice. Below it lies the question: how far down does the solid shell extend before it gives way to liquid? The answer matters because the thickness of Europa's ice controls almost everything else we want to understand. It affects how easily the ocean communicates with the surface, how heat escapes, how chemicals move, and whether material from above can reach the water below. A thin shell would allow more frequent exchange. A thick shell would make the ocean harder to reach, though not necessarily isolated. Current models do not point to one simple number. Europa's outermost ice is probably rigid and brittle. Beneath that, warmer ice may deform more easily, flowing over long periods rather than breaking suddenly. The total shell may be many kilometers thick and possibly several tens of kilometers in places. Yet thickness alone does not describe the whole structure. Ice can contain pockets of liquid. Warm regions may rise. Cold material may sink. Fractures can open, freeze, and reopen. Briny water can remain liquid at temperatures where pure water would become solid. The boundary between crust and ocean may not be a flat line. It may be uneven, changing across the Moon and through time. One of the clearest signs of this internal movement appears in regions known as chaos terrain. These landscapes look as though sections of the surface were broken apart, shifted, and then frozen into new arrangements. Blocks of ice stand at different angles. Some seem to have rotated. Others appear partly submerged in younger material. The name sounds dramatic, but the geology may have developed through slow physical processes. Warm ice could rise from below and weaken the crust. Local melting could create shallow reservoirs. Salty liquid might move into fractures and disrupt the surface. A thick shell could also convect, carrying heat upward, without requiring the global ocean to sit directly beneath every broken region. Several explanations may operate at once. Europa's surface has had time to record them. The Moon completes one orbit around Jupiter in a little more than 3.5 Earth days. During that short interval, Jupiter's gravity changes its shape by small but meaningful amounts. The crust bends. Long fractures experience repeated stress. The ocean beneath the shell helps the surface respond. Because liquid allows the outer layer to move somewhat independently from the interior. If Europa were frozen solid, its tidal response would be different. Measurements of its shape and motion therefore provide another way to test for the sea below. The ocean is thought to contain more water than all of Earth's surface ocean combined. That comparison is useful, though it can also be misleading. Europa is much smaller than Earth. Its ocean does not form a shallow covering on a large planet. It may wrap around a small moon in a layer tens, or perhaps more than 100 kilometers deep. On Earth, the average ocean depth is only a few kilometers. Europa's water may extend much farther downward. The seafloor, if the liquid reaches rock, would lie under pressures unlike those found across most of Earth's oceans. The chemistry would depend on the minerals present, the temperature of the rocky mantle, and how much circulation occurs between the water and the interior. That contact is one of the most important unresolved questions. If Europa's ocean meets a rocky seafloor, water-rock reactions could provide chemical energy. Tidal flexing may warm the rock as well as the ice. Fractures within the mantle could allow heated water to circulate. Some models permit hydrothermal activity, but there is not yet direct evidence for active vents on Europa. The possibility is supported by physical reasoning, not by a sampled plume or photographed seafloor. Scientific caution becomes especially important here. Europa contains liquid water. It likely contains salts. It receives energy through tides. Its surface carries oxidized chemicals created by radiation from Jupiter's magnetosphere. These facts make it an important environment for studying habitability. They do not show that the ocean contains life. The difference between a promising environment and a living one remains immense. The radiation at Europa's surface is intense. Jupiter's magnetic field traps charged particles and accelerates them through the space around the planet. Europa moves through this environment continuously. The particles strike the ice and alter the molecules they encounter. Water can be split into reactive fragments. Sulfur and other materials deposited from nearby space can be trapped. Compounds containing oxygen may accumulate near the surface. For any possible organisms below, these products could become chemically useful if they are transported downward. The challenge is the journey. Radiation chemistry occurs mainly at the top. The ocean lies far beneath. Some process must connect the two. Surface ice may be carried downward through geological recycling. Fractures may allow brines to rise and later sink. Impacts can mix material. Convective motion within warmer ice could gradually move oxidants toward deeper layers. No single pathway has been confirmed as dominant. The rate of exchange may be very slow. Yet Europa has existed for billions of years. A process that moves only a small amount of material during a human lifetime can still reshape the chemistry of an ocean over geological time. This is one reason the age of the surface matters. Europa has fewer large craters than many neighboring moons. That suggests its exterior has been renewed more recently, though estimates of the exact age depend on models of impact rates in the outer solar system. A younger surface means older terrain has been removed, altered, or covered. The moon has not remained fixed. Something continues to erase part of its history. That something may include new ice rising from below, fractures opening and sealing, or regions being rearranged by internal warmth. The ocean is hidden, but the crust above it is active enough to leave clues. Some observations have also suggested that water vapor may occasionally appear above Europa. Evidence for plumes has been reported from ultraviolet observations and from reanalysis of spacecraft data. The signals are intriguing, but they have not produced the same clear and repeatedly sampled picture seen at Enceladus. If plumes occur, they may be intermittent. They may arise from shallow reservoirs rather than directly from the global ocean. They may be difficult to detect because they are small, brief, or present only under certain conditions. For mission planners, the uncertainty matters. Flying through a plume would offer access to fresh material without landing. But designing an entire investigation around a feature that may not appear on schedule would carry risk. Europa therefore demands several methods at once. A spacecraft can map the surface in greater detail. It can measure the moon's gravity. It can study the magnetic response. It can use radar to probe the ice. It can search for warm regions. It can examine the chemistry of material on the surface. Together, these measurements can constrain the thickness of the shell and identify places where recent exchange may have occurred. The Europa Clipper mission was developed for this broader approach. Rather than entering orbit around Europa itself, the spacecraft is designed to travel around Jupiter and make repeated close flybys of the moon. This path limits long exposure to the strongest radiation, while allowing many observations from different positions. Each pass can reveal another part of the system. Radar measurements can test the structure of the ice. Cameras can map fractures and disrupted terrain. Spectrometers can identify surface compounds. Magnetic and plasma instruments can study the ocean's electrical signature. Gravity measurements can help reveal how mass is distributed inside the moon. No single instrument will open the sea, but many instruments, returning again and again, can narrow the range of what lies below. The goal is not to detect life directly. It is to determine whether Europa possesses the conditions that could support it. That means understanding the water, the chemistry, the energy, and the stability of the environment over time. A world may contain all the correct ingredients and still remain lifeless. Another may have produced biology through a path we do not yet know how to predict. Before such questions can be approached carefully, the physical setting must be understood. Europa gives us an ocean without a visible shoreline. Its surface is not separate from that ocean. It is the upper boundary of the same system. Radiation changes the top. Tides deform the shell. Warmth rises from within. Salts move through cracks. The orbit around Jupiter supplies energy to a sea that sunlight cannot reach. There may be no open water anywhere on the Moon, no place where a wave meets air, no weather passing above the liquid. If motion exists in the ocean, it may be driven by heat, rotation, chemistry, and the changing pull of Jupiter. Currents could move beneath kilometers of ice. Minerals could dissolve near the bottom. Reactive compounds could descend from above. All of it would occur without a horizon. And above that enclosed sea, the frozen surface keeps a partial record of what the water cannot show directly. Every ridge is a piece of stress. Every disrupted plane is a piece of heat. Every magnetic variation is a piece of conductivity. The ocean is reconstructed from effects. It becomes visible only through the ways it changes everything around it. Europa's sea does not rise into sunlight. Instead, it writes itself into the ice. Ganymede carries its ocean beneath the surface, much older than Europa's. The Moon is enormous by comparison with most natural satellites. It is the largest moon in the solar system, wider than Mercury, and nearly as large across as Mars, though far less massive than either planet. Its surface is divided between two broad kinds of terrain. Some regions are dark and heavily cratered, preserving a record of impacts from the early solar system. Other regions are brighter, crossed by grooves and ridges that suggest the crust once stretched and shifted. The Moon has not been completely inactive, but its surface does not show the same degree of recent renewal seen on Europa. Ganymede's hidden water is revealed in other ways. One of the most important came from its magnetic field. Ganymede is the only moon known to generate a substantial magnetic field of its own. Deep inside, movement within a metallic core is thought to produce it, much as motion in Earth's liquid outer core creates the magnetic field surrounding our planet. This gives Ganymede a small magnetic environment nested inside Jupiter's much larger one. The result is unusually complex. Charged particles moving through Jupiter's magnetosphere interact with Ganymede's own field. Beneath the ice, a salty ocean responds as well. The electrical currents induced in that water alter the magnetic signals measured around the Moon. By separating these overlapping effects, scientists have been able to test models of the interior. The observations support a broad layer of conductive liquid beneath the surface. Later measurements added another clue. Ultraviolet observations of Ganymede's auroral bands showed that their positions shift as Jupiter's magnetic field changes around the Moon. If Ganymede were solid throughout, those bands would move more than they do. A conductive ocean dampens the motion. The water acts like an electromagnetic buffer, generating a response that resists part of the changing field. The auroras remain closer to their average positions because the ocean below is carrying electrical currents. A movement in the upper atmosphere becomes evidence for water buried far beneath the crust. The likely ocean on Ganymede may be deeper than Europa's and arranged in a more complicated structure. Pressure increases as depth increases. On Earth, water remains liquid across most of the ocean because the pressure is not high enough to force it into unfamiliar solid phases. Inside a much larger, icy moon, The weight of the overlying water and ice can become great enough to change the crystal structure. Water ice does not have only one form. The ice in a glass or a frozen lake has a familiar open structure that makes it less dense than liquid water. This is why ordinary ice floats. Under high pressure, water molecules can arrange themselves more tightly. The resulting phases of ice are denser. They would sink rather than rise. Inside Ganymede, this may create several stacked layers. Ordinary ice could form the outer shell. Below it may lie a liquid ocean. Farther down, pressure could produce a dense layer of high-pressure ice. Below that, depending on temperature, composition, and depth, another liquid layer may appear. Still deeper, another solid phase may form. The exact arrangement remains uncertain, but the general idea is well supported by the physics of water under pressure. Ganymede may not contain one simple ocean. It may contain a sequence of liquid and solid water layers extending through much of the Moon's interior. In some models, the total amount of water is immense. Even though most of it is hidden, the combined volume may exceed the water held in Earth's oceans by a wide margin. But volume alone does not determine habitability. The location of the water matters. An ocean-touching rock can receive minerals and chemical energy from below. An ocean trapped between layers of ice may have fewer pathways for this exchange. This has led to the idea that high-pressure ice could create a barrier between water and the rocky mantle. If the lowest liquid layer rests directly on dense ice instead of rock, reactions at the seafloor would be limited. The ocean might still contain dissolved salts and compounds inherited from earlier stages of formation. Material could move between layers through cracks, melting, and slow circulation. But the direct contact that makes Europa and Enceladus so interesting might be reduced. Recent interior models have made the picture less rigid. Salts can change where different ice phases form. Heat from the rocky interior can alter the boundaries. Convection may carry material across layers over long periods. A dense, salty liquid could settle beneath a layer of high-pressure ice, allowing at least part of the water system to touch rock. The internal arrangement may be dynamic rather than perfectly separated. This matters because Ganymede has existed for more than 4 billion years. A small exchange repeated across such a span can move a great amount of material. Even a barrier that appears complete on a diagram may behave differently when warmed, stressed, and mixed over geological time. Ganymede also carries evidence of a differentiated interior. Dense material sank toward the center early in its history, producing a metallic core surrounded by a rocky mantle and outer layers rich in water. This separation required heat. Some of that heat came from radioactive decay. Some came from impacts and compression during formation. Earlier orbital interactions may also have contributed. The Moon's present state is the result of a long thermal history. The ocean may be a surviving remnant of that warmth, preserved by insulating ice and sustained by ongoing energy from the interior. Unlike Europa, Ganymede is not strongly heated by tides today. Its orbit around Jupiter is less eccentric, so the repeated change in gravitational stress is smaller. The Moon still participates in the orbital resonance linking Io, Europa, and Ganymede, but its present tidal heating is more modest. This gives Ganymede's ocean a different origin story. Europa's sea is closely tied to continuing flexure. Ganymede's may depend more on its size, internal heat, dissolved salts, and the slow loss of energy through a thick outer shell. Two moons can orbit the same planet and preserve water in different ways. That difference broadens the search. It means hidden oceans do not require one exact arrangement. They can be maintained by several combinations of heat, pressure, chemistry, and insulation. Ganymede's great size also affects how it has changed. Its interior pressure is higher. Its core may remain active enough to sustain a magnetic field. its water layers can reach forms that smaller moons may never produce. Its surface gravity is stronger than Europa's, though still much weaker than Earth's. Every layer responds to these conditions. The ice does not behave as a single rigid covering. Over long spans, warm ice can flow, dense phases can convect, liquid layers can transport heat. The moon's magnetic field can direct charged particles toward particular regions of the surface. All of these processes are linked. The hidden ocean is not an isolated chamber. It belongs to an entire planetary body. Above it, the surface preserves both great age and signs of change. The darker terrain is crowded with impact scars. Some craters are surrounded by bright material excavated from below. Others have relaxed shapes, suggesting the icy crust responded to pressure over time rather than remaining completely rigid. The brighter grooved regions record episodes when the crust was pulled apart and resurfaced. These events may have occurred long ago, when the interior was warmer and the shell more mobile. Today, Ganymede appears less active than Europa or Enceladus, but reduced activity does not mean the interior has frozen. A moon can carry a liquid layer without producing plumes or rapid surface renewal. Its ocean may persist beneath a crust that changes only gradually. The European Space Agency's Jupiter Icy Moons Explorer was designed in part to investigate this world. The mission is planned to study Jupiter's icy moons, with particular attention to Ganymede. After a series of flybys, the spacecraft is intended to enter orbit around the moon. That would make Ganymede the first moon, beyond Earth's own, to be orbited by a dedicated spacecraft. From there, instruments can examine the magnetic environment, gravity field, surface composition, ice structure, and interaction with Jupiter's magnetosphere. Repeated measurements from orbit can reveal details that brief flybys cannot. Small changes can be tracked over time. The shape of the magnetic response can help constrain the depth and conductivity of the ocean. Radar can test the upper ice. Precise tracking of the spacecraft can reveal how mass is distributed inside the moon. Surface mapping can connect old fractures and grooved terrains with interior models. The goal is not merely to confirm that water exists. The stronger question is how the whole moon works. How many liquid layers are present? Where do they begin? Do any touch rock? How thick is the outer shell? How does heat move upward? How does the magnetic field interact with the ocean? These questions turn Ganymede into more than a larger version of Europa. Its structure may represent a separate class of ocean world. Europa offers a global sea beneath a relatively thin outer shell, driven strongly by tides. Enceladus offers a smaller ocean that reaches space through active fractures. Ganymede may hold a deep, layered water system shaped by pressure and protected beneath an old surface. The contrast is useful. It shows that the phrase "ocean's moon" can hide many different interiors. Some oceans sit directly above rock. Some may be divided by dense ice. Some communicate with the surface. Some may remain sealed for long intervals. Some are warmed mainly by orbital flexing. Others survive through size, insulation, and internal heat. The word ocean suggests familiarity. It brings to mind open water, weather, shorelines, and light. On Ganymede, almost none of those images apply. The water may be enclosed between substances that are themselves made of water. A liquid layer may have ice above it and another kind of ice below it. There may be no seafloor in the usual sense. There may be no single bottom. The sea could be part of a vertical sequence extending through hundreds of kilometers, with each boundary defined by pressure rather than geography. For any hypothetical organism, the world would be local. It would not know the moon as a sphere. It would know temperature, chemistry, current, mineral content, and the boundaries of the liquid around it. The great magnetic field above, the cratered surface, Jupiter filling the sky, and the wider solar system would have no direct presence there. Only the consequences would arrive. a trace of heat from the core, a change in pressure, a dissolved ion, a current moving through enclosed water. From orbit, Ganymede appears solid. Inside, water may be arranged in layers deeper than continents are wide. The moon hides not one sea, but an entire architecture of water. Titan hides water beneath a surface that appears, at first, to be ruled by something else. From orbit, Saturn's largest moon is wrapped in a thick, orange atmosphere. The haze conceals the ground from visible light, softening the moon into a muted sphere without clear detail. Beneath that atmosphere lies one of the most Earth-like landscapes found beyond Earth. There are river channels, there are rounded pebbles, there are dunes stretching across broad equatorial regions. Near the poles, there are lakes and seas with shorelines shaped by liquid. But the liquid on Titan's surface is not water. It is mainly methane and ethane. At Titan's temperature, water ice behaves more like rock. It forms the ground, the hills, and perhaps the material carried along riverbeds. Methane moves through the atmosphere in a cycle that in some ways resembles the movement of water on Earth. It evaporates, it gathers in clouds, it falls as rain, it flows across the surface and collects in low basins. Titan therefore presents two different kinds of ocean world at once. Above, hydrocarbons move beneath an open sky. Below, water may remain enclosed beneath ice. Evidence for the internal ocean comes from several directions. Titan's surface rises and falls slightly as the moon travels around Saturn. The degree of deformation is difficult to explain if the interior is completely solid. A liquid layer beneath the crust allows the outer shell to flex more easily under changing gravitational forces. Measurements of Titan's gravity also suggest that its interior is divided into layers. There is likely a rocky center. Around it may lie dense forms of high-pressure ice. Above those layers, a broad ocean of water mixed with dissolved compounds may remain liquid. The outer shell forms the cold surface. As on Ganymede, the water may not touch rock directly. High-pressure ice could separate much of the ocean from the deeper rocky interior. That separation would limit some chemical exchanges, but Titan's ocean may contain ammonia or other substances that help lower the freezing point of water. Salts may also be present. These materials would influence density, conductivity, and the way heat moves through the interior. The composition remains uncertain. So does the depth. The ocean may begin tens of kilometers below the surface, beneath a crust thick enough to isolate it from the methane weather above. Yet complete isolation is not guaranteed. Titan's surface includes mountains, broad plains, impact features, and regions that may have been altered by internal activity. Some landforms have been interpreted as possible cryovolcanic structures, where water-rich material might have risen from below instead of molten rock. The evidence is not decisive. Surface features on Titan are difficult to interpret because erosion, sediment, wind, and haze can reshape the landscape. A rounded hill may have formed through internal uplift. It may also have been carved or covered by later processes. A depression may record an explosion, a collapse, or the dissolution of surface material. Titan does not preserve one clear story. It preserves several processes written across the same terrain. The atmosphere adds another layer. Nitrogen dominates the air. Methane, though present in much smaller amounts, drives much of the visible weather and chemistry. High above the surface, sunlight and energetic particles break methane and nitrogen apart. Their fragments combine into more complex carbon-bearing molecules. Some gather into haze particles and settle slowly downward. Over time, Titan receives a continuous fall of organic material from its own sky. This makes the moon chemically rich. But richness alone does not make a habitat. The surface is extremely cold. Reactions occur more slowly than they do in warm liquid water. The hydrocarbon lakes provide solvents, unlike the water used by all known life. It is possible to imagine unfamiliar chemistry operating in such an environment, but there is no evidence that biology exists there. The more familiar setting for habitability would be the buried water ocean. The difficulty is connection. Organic molecules form in the atmosphere and accumulate on the surface. Liquid water lies far below. For those materials to interact, some pathway must carry surface chemistry downward or bring water upward. Large impacts may provide temporary contact. When an object strikes Titan, it can melt water ice and create a warm liquid environment that lasts until the melt refreezes. Surface organics mixed into such a region could enter water and undergo reactions that are otherwise impossible in the cold methane landscape. Cryovolcanism, if it occurs, could provide another route. Fractures might allow water-rich material to approach or reach the surface. Over long intervals, parts of the crust could overturn or recycle. Each pathway remains uncertain in scale and frequency. Titan may therefore possess the ingredients for interesting chemistry while keeping them in separate places. Carbon compounds above, liquid water below, energy distributed unevenly between them. The moon becomes a study in boundaries. On Earth, the atmosphere, oceans, crust, and living systems exchange material continuously. On Titan, some of the same broad categories exist, but the connections may be weaker, slower, or more occasional. A world can contain several promising environments without combining them in a useful way. Titan's hidden sea also differs from Europa's in temperature and energy. Europa is strongly flexed by Jupiter. Enceladus releases heat near its south pole. Titan experiences tides, but its larger size, thick ice shell, atmosphere, and different orbital setting create another thermal history. Its interior may retain warmth from formation and radioactive decay. The ocean may cool gradually over time. If ammonia is mixed into the water, it can remain liquid at lower temperatures, prolonging the life of the sea. The ocean may also be dense enough to affect how Titan rotates. The outer shell is not perfectly fixed to the deeper interior. Liquid allows some degree of separation, so the crust can respond to atmospheric winds and Saturn's pull without carrying the entire moon with it. Even the movement of the atmosphere may influence the rotation of the surface by tiny amounts. The sea below becomes part of that response. It is unseen, yet it changes how the moon moves. Beyond Titan, other moons offer less obvious possibilities. Callisto appears heavily cratered and comparatively inactive. Its face preserves impact basins and overlapping scars from early solar system history. There are no known plumes. There is no clear evidence of ongoing resurfacing on the scale seen at Europa. Still, magnetic measurements indicate that a conductive layer may lie beneath its crust. The simplest explanation is a salty ocean. Callisto's liquid may survive because dissolved materials reduce the freezing temperature, while the thick outer shell slows the loss of heat. Radioactive decay within the rocky interior may provide part of the remaining energy. Tidal heating is weaker than on Europa because Callisto lies farther from Jupiter and does not participate in the same close orbital resonance. Its ocean, if present, may be old, cold, and comparatively isolated. That makes Callisto important for a different reason. It shows that hidden seas may persist without dramatic activity. A moon does not need to display jets or fresh ice to contain liquid. It may hold water beneath a surface that has looked nearly unchanged for billions of years. Mimas offers an even more surprising case. This Norse moon of Saturn is best known for a large impact crater that gives it a familiar, heavily battered appearance. For many years, it seemed like an unlikely place to search for liquid water. Its surface does not show the bright fractures of Enceladus. There are no known plumes. Its old terrain suggests limited recent geological activity. Yet, careful measurements of its rotation and orbital motions have led researchers to consider the presence of a buried ocean. a solid moon should wobble in one way. A crust separated from the interior by liquid can wobble differently. The observed behavior is consistent with an ocean beneath a thick shell, though models of the interior continue to be refined. If Mimas does contain liquid water, the ocean may be geologically young. That possibility changes how ocean worlds are understood. An ocean need not be a feature preserved since the earliest formation of a moon. It may develop later as tidal heating changes, as orbital relationships evolve, or as internal conditions cross a threshold. A frozen interior can begin to melt. A previously solid moon can enter an ocean-bearing phase. The reverse is also possible. An ocean can gradually freeze when heat declines. Hidden seas may therefore be temporary on cosmic timescales, even if they endure for millions or hundreds of millions of years. This creates a wider picture of the outer solar system. Some moons may have carried oceans in the past. Some carry them now. Some may develop them later. The category is not fixed. It depends on orbital history, internal structure, dissolved materials, and the slow movement of energy. Triton, the largest moon of Neptune, may also contain an ocean. Its surface is young in places and shaped by processes that suggest internal activity. It moves around Neptune in the opposite direction from the planet's rotation, evidence that it was probably captured rather than formed in its present orbit. That capture would have produced intense tidal heating in the past. Some of that thermal history may still influence the interior. Pluto, though classified as a dwarf planet rather than a moon, offers a related example. Its surface geology suggests that a subsurface ocean may have persisted beneath the crust. The broad basin known Sputnik Planitia and the distribution of mass around it have been studied as possible evidence for liquid water below. These distant worlds extend the pattern beyond the large moons of Jupiter and Saturn. The farther exploration moves, the less unusual buried water begins to seem. The old idea placed oceans only on warm surfaces near a star. The newer picture allows them beneath ice, protected from space, warmed by gravity, pressure, chemistry, and the remaining heat of formation. The surface can mislead. A cratered moon may hide liquid. A world with methane rain may conceal water below. A small body that appears frozen through may still be changing inside. There is no single outward appearance that identifies an ocean world. Some reveal themselves through magnetic fields, some through plumes, some through a wobble, some through the shape of a basin or the timing of an orbit. The sea is discovered through its consequences, and each new candidate makes the solar system feel less like a collection of dry worlds separated by empty space. Beneath many of its coldest surfaces, water may still be moving. To search for life in a hidden ocean, scientists first have to decide what evidence would mean. This is harder than it sounds. A spacecraft can measure water. It can detect salts, carbon-bearing molecules, hydrogen, phosphorus, and other elements involved in life on Earth. It can find heat. It can identify chemical imbalances that might provide energy. But none of these alone is biology. The same planet or moon can produce complex chemistry without ever producing an organism. Rock and water can react. Radiation can build and break molecules. Heat can rearrange compounds into patterns that appear suggestive until a non-living process explains them. The search therefore begins with habitability. Does liquid water exist? Has it remained stable long enough for complicated chemistry to develop? Is there a source of energy that can be used rather than merely lost as heat? Are the necessary elements available? Can materials circulate, bringing reactants together and carrying waste products away? These questions are more modest than asking whether something is alive. They are also more answerable. Enceladus currently offers the most accessible ocean material. Its plume carries particles from beneath the surface into space, allowing a spacecraft to sample them during a flyby. A future mission could pass through the jets at a lower speed than Cassini, reducing damage to delicate molecules and improving the chance of preserving their structure. The instruments could search for amino acids. They could examine lipids or other membrane-like compounds. They could measure whether certain molecules appear in proportions that are difficult to explain through ordinary geochemistry. They could compare isotopes, the slightly different forms of elements whose ratios can sometimes record how a reaction occurred. On Earth, life often favors particular isotopes because biological reactions process lighter and heavier atoms at different rates. But isotope patterns are not automatic proof. Non-living chemistry can also separate isotopes. The environment must be understood well enough to distinguish one explanation from another. The same caution applies to molecular handedness. Some organic molecules exist in two mirror image forms. Earth life often uses one form far more than the other. A strong imbalance in a fresh sample could be interesting, yet minerals, radiation, and physical sorting can also create asymmetries. No single sign is likely to settle the question. The strongest case would come from several independent lines of evidence that point toward the same biological interpretation while resisting non-living alternatives. A complex distribution of organic molecules, a consistent isotope pattern, a source of chemical energy, structures that resemble products of metabolism, repeated measurements showing that the pattern is not contamination or instrument noise. The evidence would need to fit together. Europa presents a different challenge. Its ocean may be harder to sample directly, but material from below could be carried upward and preserved within the surface ice. A lander placed in a geologically young region might collect grains that reach the surface more recently than the older radiation-altered material nearby. Even then, the top layer would have been exposed to Jupiter's radiation. Organic molecules can be broken apart or transformed there. The freshest material may lie below the immediate surface, requiring a drill or scoop to reach ice that has been partly shielded. The depth needed would depend on local radiation, burial history, and the age of the deposit. A sample from Europa would also carry another difficulty. Surface chemistry does not necessarily represent ocean chemistry directly. Material may be altered while rising through the shell. Water can freeze and leave salts behind. Different compounds can separate. Radiation can create new molecules after deposition. A plume, if one is found and sampled, might come from a shallow pocket rather than the global ocean. Every sample has a history. Understanding that history is part of understanding what it contains. The most ambitious concept would be to pass through the ice itself. A robotic probe could melt downward, carrying instruments through kilometers of frozen crust until it reached liquid water. A second vehicle might then move beneath the shell, examining the ocean directly. The idea is physically possible. It is also far beyond the simplicity suggested by a drawing. The probe would need enormous energy. It would have to prevent melted water from refreezing around it. It would need to communicate through thick ice or leave a cable behind. It would have to survive pressure, cold, salts, and an environment that no machine has entered. Most difficult of all, it would have to be exceptionally clean. Earth organisms can survive in places once assumed sterile. Some endure cold, radiation, dehydration, and long periods without nutrients. A spacecraft carrying even a small number of hardy microbes could introduce them into an ocean that may have remained isolated for billions of years. That would create two losses at once. It could disturb an environment we are trying to understand, and it could make later discoveries ambiguous. A living cell found beneath Europa's ice would mean very little if there were a chance it had traveled from a laboratory on Earth. Planetary protection is therefore not only about caution, it is about preserving the meaning of evidence. The cleaner the mission, the more confidently a future result can be interpreted. This concern becomes sharper because life in a buried ocean may not resemble the forms people first imagine. There may be no forests of unfamiliar plants, no large creatures moving through open water, no visual scene that a camera could easily recognize. If life exists, it may be microbial. It may live within pores in rock. It may gather near chemical gradients where one substance meets another. It may grow slowly in water with limited energy, dividing far less often than microorganisms in warmer environments on Earth. An ecosystem can be alive without being abundant. It can persist in thin films. It can occupy only a small fraction of the ocean. A spacecraft could sample a great volume of water and still miss it. This changes how absence must be interpreted. A mission that finds no biological signal has not necessarily shown that the ocean is sterile. It may have sampled the wrong place. The signal may be too faint. The organisms may live only near the seafloor, while the plume carries mostly surface water from the top of the ocean. The chemistry may use structures unfamiliar to instruments designed around terrestrial life. Negative evidence becomes meaningful only when the limits of detection are known. The same is true on Earth. A cup of water taken from the middle of an ocean cannot describe every ecosystem on the seafloor. A sample of air cannot reveal what lives kilometers underground. Hidden ocean missions will face the same problem on a larger scale. The seas themselves may be active in ways that determine where life could gather. Heat rising from the interior can drive circulation. Rotation can organize currents. Dissolved salts can create layers of different density. Water near the ice may cool and sink. Warmer water near rock may rise. If chemical reactions occur at the bottom, their products may be transported upward slowly, diluted through the ocean, or trapped in local regions. A plume provides access but also a filter. Only material that enters the correct fractures reaches space. Large particles may settle. Fragile molecules may break. Gases may separate from liquids. The sample is valuable because it comes from within, yet it is not the entire ocean. Scientists can prepare for this by building models before the spacecraft arrives. Laboratories can recreate high-pressure water, salty ice, mineral reactions, and plume formation. Researchers can test how molecules survive freezing and acceleration. They can study terrestrial environments where life persists without sunlight. Deep ocean vents are one example, but not the only one. Microorganisms live within rock. They survive beneath glaciers. They use hydrogen, sulfur, iron, methane, and other substances in reactions that do not depend directly on photosynthesis. These ecosystems expand the range of possibilities. They also remind us that analogy has limits. Europa is not Earth beneath ice. Enceladus is not a smaller version of an earthly ocean. Their chemistry, pressure, gravity, and history are their own. The purpose of terrestrial examples is not to predict exactly what will be found. It is to show that sunlight is not the only path to metabolism, and that water-rock chemistry can support living systems under the right conditions. The deeper question concerns origins. Even if a moon contains a habitable ocean, did life ever begin there? On Earth, the transition from chemistry to biology remains incompletely understood. We know that life appeared early in the planet's history, but the exact pathway is still being studied. A hidden ocean may possess water, energy, and organic compounds without crossing that threshold. It may remain chemically active, but lifeless for billions of years. Or the origin of life may occur readily when conditions are suitable. One confirmed example beyond Earth would change the scale of the question. If life began independently in an ocean beneath ice, then biology would no longer appear tied to warm planetary surfaces under open sunlight. It would belong to a wider class of environments. The galaxy contains many planetary systems. Large planets with icy moons may be common, free-floating worlds far from any star. could retain internal oceans beneath insulating shells. Dwarf planets and distant bodies may preserve water through heat and dissolved compounds. A discovery in one small moon would therefore point beyond that moon. But the search cannot begin with the conclusion. It must begin with measurements careful enough to survive doubt. A signal must be repeated, contamination must be excluded, geochemistry must be tested. The limits of the instrument must be known. Uncertainty must remain visible until the evidence narrows it. This patience is not a weakness in the search. It is what protects the search from finding what it hoped to find. Beneath the ice, there may be living chemistry. There may also be only water, rock, heat, and time. For now, both possibilities remain open. The next generation of ocean world exploration will not begin by entering the water. It will begin by reducing uncertainty. Before a spacecraft can approach a hidden sea, scientists need a better map of the barriers above it. They need to know where the ice is thick, where it has been disrupted, how heat moves through it, and which regions may preserve material from below. This is the work of orbiters and repeated flybys. A single close pass can reveal a great deal, but an ocean world changes with position and time. Magnetic fields vary. Fractures respond to tides. Plumes may strengthen or fade. Surface temperatures shift as a moon moves through its orbit. Returning again and again allows those patterns to separate from noise. Europa Clipper is intended to make dozens of close approaches to Europa while remaining in orbit around Jupiter. Each encounter will view the moon under different conditions and from a different geometry. Some passes will favor imaging. Others will improve gravity measurements. Radar observations will probe the upper crust. Spectrometers will examine salts, ice, and compounds altered by radiation. Magnetic instruments will study the conductive response of the ocean below. No observation will stand alone. A region that appears young in images can be compared with its temperature, chemistry, and subsurface structure. A possible water deposit can be tested against models of radiation exposure. A change in the magnetic field can be examined alongside Europa's position in Jupiter's magnetosphere. The moon will gradually become a connected physical system rather than a collection of separate clues. The Jupiter Icy Moons Explorer will approach the same planetary system with a different emphasis. Its journey includes encounters with Europa and Callisto, but Ganymede is its main destination. Entering orbit around Ganymede will allow the spacecraft to study one ocean world for an extended period. This matters because Ganymede's signals overlap. Its own magnetic field interacts with Jupiter's. Its ocean produces an induced response. Charged particles create auroras and alter the surface. Its gravity field carries information about several deep layers. Long observation can help distinguish these effects. The spacecraft path can be tracked with great precision. Small accelerations reveal variations in the moon's mass distribution. Combined with magnetic and surface measurements, those variations may show whether the ocean forms one main layer or part of a more complicated stack. Radar may reveal structures within the upper ice. It will not pass through the entire moon, but it can identify boundaries, buried features, and changes in material that help constrain how the crust developed. The larger goal is comparison. Europa, Ganymede, and Callisto formed in the same broad region around Jupiter, yet their interiors followed different paths. Europa remained strongly active. Ganymede differentiated deeply and generated a magnetic field. Callisto preserved an older exterior and may never have separated internally as completely. Studied together, they offer a natural experiment in how size, composition, orbital position, and heat determine the fate of water. At Saturn, future mission concepts often turn toward Enceladus. The reason is practical as well as scientific. The ocean is already sending samples out. A spacecraft could fly through the plume. many times, collecting material at different heights, speeds, and positions above the fractures. It could compare vapor with ice grains and test whether certain compounds are concentrated in particular particles. Lower encounter speeds would help preserve large molecules. More capable mass spectrometers could distinguish compounds that Cassini could only register broadly. The mission could search not merely for organic material, but for organized chemical patterns. It could examine whether carbon compounds form a smooth distribution expected from non-living reactions, or whether certain sizes and structures appear with unusual frequency. It could study amino acids without assuming that their presence alone is biological. It could measure isotopes across several elements. It could look for repeated combinations that become meaningful only when taken together. Even a powerful instrument would face limits. The plume may alter the ocean sample. Water boiling into space can separate compounds. Ice grains can form at different depths. Some material may come from the walls of fractures rather than the sea itself. A future mission would therefore need to study the plumbing as carefully as the chemistry. The timing of each pass would matter. So would the altitude above the surface. A sample collected near the plume source may differ from one gathered after particles have traveled farther into space. Mapping those differences could reveal how the material changes during its ascent. Titan requires another approach. Its thick atmosphere and complex surface make it a world where movement through the sky can be as valuable as movement around the moon. The Dragonfly mission is designed as a rotorcraft capable of traveling between locations on Titan's surface. Its primary investigations concern surface chemistry, geology, and habitability, rather than direct access to the deep ocean. Even so, the mission may help explain how material moves between Titan's atmosphere, crust, and interior. It can examine organic deposits created in the atmosphere. It can study impact sites where water ice may once have melted. It can measure the composition of surface materials in environments shaped by methane, rain, and wind. An impact crater is especially useful because it may have brought deeper water-rich material closer to the surface. For a limited period after the impact, liquid water could have mixed with organic compounds that had accumulated above. The resulting chemistry may have been preserved after the region froze again. Such a site cannot reveal the present ocean directly. It can show what happens when Titan's separate chemical layers briefly meet. This is part of a wider strategy. Not every mission must reach liquid water to teach us about an ocean world. The surface contains material processed by the interior. The atmosphere records exchange with the ground. Rotation reveals whether the crust is detached from deeper layers. Gravity reveals density. Magnetism reveals conductivity. Heat reveals energy escaping upward. Each method sees a different consequence of the same hidden structure. Eventually, more direct exploration may become possible. One concept involves a lander near Enceladus's south pole, where plume particles settle back onto the surface. Fresh deposits could be collected without crossing the jets at high speed. Another concept would return plume material to Earth. A sample return mission could place ice grains inside a sealed container and bring them to laboratories with instruments too large and complex to send across the solar system. The scientific value would be immense. So would the challenge of preserving the sample. Volatile compounds could escape. Molecules could react during the journey. Radiation could alter delicate structures. The container would need to prevent contamination in both directions. Material from Enceladus would have to remain isolated from Earth. Earth's environment would need protection from the sample until its nature was understood. These requirements would shape the entire mission. A return capsule would not simply deliver ice. It would carry an unknown chemical record from another ocean. reaching Europa's water directly would be harder. A surface mission would first need to survive radiation and extreme cold. It would need to operate on fractured terrain where landing hazards may be difficult to see from orbit. A drill could reach shielded ice below the radiation-damaged surface. A melting probe could descend farther, but the energy demand grows with every kilometer. The ice above the ocean may not be clean or uniform. Dust, salts, voids, and embedded blocks could interrupt the path. The probe would have to recognize obstacles and respond without immediate guidance from Earth. Communication would become weaker as the ice thickened around it. A cable might link the descending vehicle to the lander, carrying power and data downward and upward. But a cable several kilometers long would need to survive tension, refreezing, movement in the ice, and the mechanical stress of deployment. When the probe finally reached water, pressure could force liquid into the newly opened channel. The system would need to avoid freezing in place or losing contact with the surface. Then the questions of cleanliness would become unavoidable. Every component that entered the ocean would need to meet strict planetary protection standards. Heat sterilization can damage electronics. Chemical cleaning may leave residues. Radiation can degrade materials. Building a machine, both capable and clean enough, would be one of the most demanding engineering tasks ever attempted. For this reason, direct entry is likely to follow years of remote study. The best landing site must be chosen carefully. The thickness of the ice must be estimated. The geology must be understood. The risk of contaminating a potentially habitable environment must be reduced. As far as possible, patience becomes part of exploration. It may take several missions to answer what appears to be one question. An orbiter may identify a young deposit. A lander may sample the upper ice. A later mission may drill deeper. Only after those steps could a probe attempt the ocean itself. Human lifetimes make this sequence feel long. Planetary science often moves across generations. The engineers who design one mission may not be the people who analyze the final result. Instruments are built using lessons from spacecraft launched decades earlier. Data gathered by one team become the foundation for another mission that was not yet possible when the first observations were made. The search for hidden seas already carries this generational structure. Voyager images revealed unfamiliar surfaces. Galileo strengthened the case for Europa's ocean. Cassini sampled Enceladus's plume. Later missions will ask more precise questions because those earlier spacecraft changed what could be imagined. A child who watches Europa Clipper leave Earth may one day work with measurements from a lander on the same moon. Another generation may design the first probe intended to descend through its ice. The ocean itself does not notice this pace. Europa continues around Jupiter. Enceladus continues around Saturn. Ganymede carries its layered water beneath old terrain. Titan's methane rain falls over a sea hidden below another sea. The worlds remain in motion while human understanding approaches by stages. We do not reach them all at once. We learn first how to listen to their gravity, their magnetism, their heat, and the particles they release. Then we move closer. The moons that hide oceans do not look alike. Europa is scored with long fractures beneath Jupiter's radiation. Enceladus releases part of its sea into space. Ganymede may hold several layers of liquid and compressed ice beneath an old surface. Titan keeps methane lakes above and water far below. Callisto, Mimas, Triton, and other distant worlds suggest that buried seas may exist, even where the exterior offers little sign of change. The shared feature is not appearance, it is protection. Ice separates liquid water from the cold of space. It slows the escape of heat. It creates pressure. It allows an interior to remain active long after sunlight has become too weak to keep water open at the surface. For centuries, oceans were imagined as planetary features shaped mainly by distance from the sun. Too near, and water would be lost to heat. Too far, and it would freeze. That picture remains useful for exposed surfaces, but it does not describe everything that can happen below them. A moon can carry its own source of warmth. An orbit can flex rock and ice. A large interior can release heat through radioactive decay. Dissolved salts can delay freezing. A thick shell can preserve energy for immense spans of time. Liquid water can survive where no human eye would expect to find it. This changes the map of potentially habitable environments. The traditional habitable zone describes the region around a star where a planet with suitable conditions might hold liquid water at its surface. Hidden oceans do not always follow that boundary. They can exist far outside it. A moon may circle a giant planet in a region where sunlight is faint, while gravity supplies enough internal energy to maintain water below. A free-floating world, moving between stars, might also preserve a buried sea beneath insulating ice. The galaxy could contain many environments where water remains liquid without blue skies or daylight. That possibility does not make life inevitable. It makes the question wider. Earth offers only one confirmed example of biology. Here, life depends on liquid water, carbon chemistry, energy, and a long history of environmental change. These features guide the search because they are the only working example available. But the ocean moons remind us that familiar ingredients can be arranged in unfamiliar ways. Water can exist without weather. Energy can arrive without sunlight. A seafloor can lie beneath hundreds of kilometers of enclosed liquid and ice. Chemistry can continue inside a world whose surface appears inactive. The first discovery of life beyond Earth, should it ever come, may not be a signal from a distant civilization or a visible organism crossing an alien landscape. It may be a pattern inside an ice grain, a group of molecules measured more than once, an isotope ratio that resists non-living explanations, a chemical imbalance sustained within plume material. Such evidence would arrive gradually. It would be checked, challenged, repeated, and compared against every known source of error. The result might remain uncertain for years before a scientific consensus formed. That pace would suit the nature of the place. The oceans themselves have remained hidden for ages. There is no reason their history would become clear in a single observation. Even without finding biology, these moons have already changed planetary science. They have shown that small bodies can remain active. They have shown that gravity can replace part of the warmth lost with distance. They have shown that the boundary between frozen and living environments cannot be drawn from surface temperature alone. They have also revealed how much can be learned without seeing the object of study directly. No spacecraft has entered Europa's sea. No instrument has descended through Ganymede's layered water. No probe has touched the ocean floor of Enceladus. Still, their interiors have become measurable through effects at the surface and in surrounding space. A magnetic field changes, a crust wobbles, a fracture warms, a plume rises, a spacecraft shifts slightly in response to hidden mass. The unseen becomes known through what it moves. This method is not unique to ocean worlds. Much of astronomy works in the same way. Black holes are studied through nearby matter and light. Dark matter is inferred through gravity. Planetary interiors are reconstructed from waves, fields, and motion. Science often begins at a boundary where something inaccessible leaves a trace. The ice above these oceans is such a boundary. It conceals the water and records it at the same time. Every mission that approaches an ocean moon must therefore learn to read surfaces without mistaking them for the whole world. A cratered landscape may sit above liquid. A bright plane may hide recent movement. A plume particle may have traveled from rock, through water, through ice, and into space before reaching an instrument. The meaning of a sample depends on that entire path. Future explorers will refine these paths. They will map thinner regions of ice. They will measure salts with greater precision. They will test whether plume material represents the deep ocean or a shallower reservoir. They will study how radiation changes molecules at the surface. They will compare one moon with another until the differences become as informative as the similarities. Over time, the phrase ocean world may divide into many categories: tidally heated oceans, layered, high-pressure oceans, young oceans, long-lived oceans, oceans that touch rock, oceans separated from it, oceans that release material, oceans almost completely sealed. Each type will carry its own chemistry and history. The solar system may come to seem less like a set of isolated objects and more like a range of experiments in how water behaves under different conditions. On Earth, water is visible nearly everywhere. It fills the clouds, falls across land, moves through soil, gathers in rivers, and covers most of the planet's surface. Its presence is so familiar that an ocean seems inseparable from open space above it. The outer moons offer another arrangement. Their seas have ceilings. Their boundaries are ice. Their tides rise beneath frozen crusts rather than beneath a sky. Any currents move through enclosed worlds, guided by heat, rotation, salinity, and gravity. There may be places in those oceans where warm water meets mineral-rich rock. There may be broad regions with little available energy. There may be chemistry occurring now that began before the first animals appeared on Earth. There may be no life at all. Each possibility remains scientifically meaningful. A lifeless ocean would still reveal how far chemistry can develop without biology. A living one would show that the origin of life is not confined to one planet's surface. Either result would deepen the same question. What can water become when it is given energy, material, and time? For now, the answer remains beneath the ice. Spacecraft move toward these moons by long routes. Signals cross the distance back to Earth. Teams compare measurements gathered years apart. New missions inherit unfinished questions from earlier ones. The process is patient because the worlds require patience. They do not offer open horizons. They offer fractures, fields, grains, tides, and motion. Through those signs, entire seas begin to take shape. Far from the sun, beneath surfaces that appear frozen through, water continues to endure. The hidden oceans keep moving below.